All right, let's go ahead and do a classic maze. Bless you. Ooh. Are you allergic? I was going to say, are you allergic to recursion or something? So we're going to go into a maze example. All right, we go ahead and clean this up. And when I talk about a maze, is a maze. When you were a kid, you had a little puzzle. You had to start, and you went to the end, and you wanted to see if you get to the end. The simplest maze recursive one, I'm just going to do the simple one for now, is you start at the beginning. Is there a way to get to the end? Are you completely blocked off, or is there actual possibility to get to the end of the maze? There is an iterative solution to this, but there's the recursive solution, I believe, is a lot easier or cleaner. So what we're going to do, first I need to somehow define a maze. So I'll call it maze, and it'll be a double array. And let's see if I can do this correctly. We'll make it a character array. Char. So we'll have, what do we want? We want to have O for open, and then W for wall. All right, how big do we want this maze to be? Not big? All right. And then we'll make, that's the size of each array. Good. Let me make sure that syntax is correct. It's been a little while since I've done this in C++. Good morning. Must have bounds for all dimensions except the first. Okay. So 1, 2, 3, 4, 5. So we'll make it, actually we'll make it, now we'll keep it with 5. There. All right, so we're good to go. So the syntax is just to do a static initialization of a character array. Notice that even though this is a two-dimensional array, this character array exists on the stack. That's just what C++ allows you to do. That's perfectly fine. All right. So we're gonna, let's see, what should we do here? So we want to know, can we navigate from, we'll say start X, start Y, to end X, comma, end Y. We want to know if that's possible. Okay? All right. So we'll go ahead and make that a function definition. We'll do Boolean can navigate. So int sx, int sy, sy, and then int index, int end, int y. So that's what we want to know, right? But to set this up recursively, we want to go and iterate to every single position. So we need to know we're going to break this down into different pieces. And the way we're going to do that is for every individual call, you're going to first evaluate, am I allowed to be here? And if I am, if I'm not, return false, because you can't go there. Then I'm going to try and check every other direction by calling myself recursively in every other direction that is possible. And if at any point I return true, because I am at the end point, then we're done. So there's two base cases here. One is if my position is not legit, return false. If my position is the end point, return true because I found a way to get there. Okay? But that means that in our recursive call, we're going to need to keep track of our position. So int position x, int position y. So we'll go with can navigate. So base cases actually. First off, if let's see what we have. Maze. Ooh, I didn't make this multi-dimensional. I'm going to make this global just to make our lives easier. And I'm going to go ahead and define. We'll go width to be, what was it, 5, and height, that's what we got here, 1, 2, 3, 4, 5, 6, to be 6, just to make my life easy. So if first off, if maze sub position x sub py equals wall, actually we should just say does not equal open, that means we can't be here, we're going to return false, right? Not a legal move. If position x equals index and position y equals py or ey, if we are at the end, return true. Can anyone think of other base cases here? Might actually be a little hard to see the other ones. Let me do an example call here. Yeah, out of bounds. There you go. Can we go from 1, to 4, 5? Can navigate. Put this on a different line. So we have 1, 1 to 4, 5, and our initialization will be 1, 1 because that's where we're starting. Although I just realized we don't need to have the position x over here, so let me go ahead and delete that. Oops. We're going to change these variables to position x and position y. Sorry, I did not think about this one too far ahead. We'll fix that real quick. All right, so position's where we are, and ex and ey is where we're trying to get to. So can we go from 1, 1 to 4, 5? All right, and then you said the other check if we're out of bounds. So that check should probably be, where should that check be in the base cases? Where should bounds checking be?
With the maze px py, does that equal?
Right, that would be a good thing. I like to do bounds checks first. So if maze or px is less than 0, or px is greater than or equal to width, or py is less than 0, or py is greater than or equal to height, return false, right? All right, so if it's out of bounds, return false. If we're not a legal move, return false. If we're at the end, return true, we're done. Okay. So, if we're at a position, we want to be able to move the different ways. The first thing we want to do is mark as visited. And this is very important because if we don't mark our visitation, then we could be bouncing back and forth when we search. So we need to mark our position as visited. So we'll do, let's see, maze sub px sub py equals v for visited. And now we're going to recurse. Well, which ways can we go? Let's just say we can go up, down, left, right for now. So for example, we would need to do maze, or we do can navigate. Maybe we want to go to the right, so px plus 1, py with the same index and the same end y. Excuse me. And what we want to do is check if that's found, return true. In other words, if we can navigate that way, then just go ahead and return true. We don't need to return anything else. And we probably want to do that for all the other directions as well. Maybe going left. Maybe going, let's go and get rid of this. going, that would be down. And then this one would be going up. But if none of those found anything, then we return false. No paths found, return false. Okay? I mean, how's that look so far? Let's see if I did that right. Ooh, close. Defined with, I forgot to put a space. There we go, much better. Perfect. Can we go from 1-1 to 4-5? Yes. Let's see if this is actually working correctly. Let's put some walls in here. One row of walls. Nope. Let's open up something. Ooh, it failed. Let's see, 1-1. One's right here to 4-5. So we go 1, 2, 3, 4, 0. Oh, 0, 1, 2. Oh, we can't go to 4-5. I wonder why that returned true the first time. To 4-4. Ooh. I wonder what we do. Oh, I put in a 0 and not an O. There we go.
Okay. So how exactly is it going there? So we made it go to x plus 1 first, or right first, right?
Right.
So it would go from 1-1 and say I can't go to right, so I'm going to go.
Right.
It'll go left then.
Yeah, so it's going to first try going, how much time we got? Okay, good, we got plenty of time. It's going to first try going right. And what I was going to do is print this out, so every time it was called, it was going to print. And then maybe we can inspect the output. Would that help a lot right now?
Yeah.
To see how it works? Good. So let's do a print function. We'll do void print of maze. For int I equals 0, I is less than what we have the width, plus plus. For int j equals 0, j is less than the height, j plus plus. All right, then we're going to do std cout. And we're going to have maze sub I sub j, and then we'll go ahead and put in a space. And then after the end of that, we'll just do each line, put in a new line. All right. So I'm going to first put out right here, and our base case is actually on the top. I'm going to say cout. I'm going to have, ooh, oh, it's annoying to type out. All right. Can navigate px, comma space, py, comma space, px, comma space, ey, and then semicolon. And then I'm going to,
The reason I'm asking is because so we passed it to try to go right and then try to go left. So I guess I was wondering why it wouldn't just go left and right back and forth.
Good question. Let's pipe this to less. All right. So we're at can navigate, and we need to, I just realized we need to put a, after the print name, print maze, we need to put a new line right here.
Oh, really? Oh, I didn't see that.
Yeah. It's because we're doing that whole visiting thing. Okay, perfect. So we're at 1-1, which is right here. And we want to know, can we get from 1-1 to 4-4, which should be 1, 2, 3, 4, 1, 2, 3, 4, which is right here. Can we get there? Okay. So we start here. Notice on our next call, we're going to the right, but we have V. And then, you know what might actually be helpful is telling you what the code did. So we'll do cout out of bounds, returning false. We'll have this not open, returning false, and then we'll have here found the end, returning true. All right, so we'll go ahead and run that again. Perfect. And it didn't print anything out. Did I not save? Out of bounds, not open. Oh, yeah, this makes sense. So x plus 1, actually x plus 1 is going down. Sorry, sometimes I get my x's and y's confused. All right, so navigate 1, 1. We're at 1, 1. Can we go to 1, 1? Well, yes, that's actually legal. So we marked it as visited. And then we're going to call x plus 1. So notice we're doing can navigate on 2, 1. B is visited, so we can actually go there as well. So now we're going to do can navigate on 3, 1. So we're right here, we're evaluating this one. Obviously we can go to this guy. So we're going to go on 4, 1, which is right here. And can we visit that one as well? Yes. So notice it does 4, 1, sets V to 4, 1. And then tries 5, 1, but that's out of bounds, so it's going to return false. And when it's back to the V, ooh, why did it jump up? Oh, out of bounds, returning false here. Then it's gonna should jump back up to 4, 1. Why did it jump back up to 3, 1? Oh, no. If that's true, return true. 4, 1, can navigate, jumps up to 3, 1. 0, 1, 2, 3. Train 1 goes back up to this value, which I'm a little puzzled at right now, and then jumps over to 4, 2. Why is this 3? Jumps back to 4, 2. Now 4, 2 makes sense because at 4, 2 you're evaluating 4 and then you're going to jump over to this wall which is not open, so you're going to go on from there to 4, 0, which is going to evaluate this right here, which turns out to be correct. So it's going to put a V right there, and then it's going to jump down 1 to try and navigate 5, 0, and find out that's not correct. There's some printing error right here. I do not know why it's printing off a 3. Because that should definitely be a 4. Oh, because it jumps up 1. Oh, I see what happens. Notice after we try going down 1, we try going up 1 afterwards. So that's why it jumps up to the 3, 0. Because it's going down, up, down, up, down, up. Now that makes sense. But do you see what it's doing? It's just recursively trying to get to every single point.
And so it can't visit somewhere where there's already a V.
Yes.
I guess the only thing, I do understand what you're saying. I guess the only thing I was wondering is, like, so we start at 1, 1, and there's a V at 1, 1.
Right.
So say you had put in the checks to go left first, and then up, and then to the right. Did you get stuck in that corner?
No, because eventually you'll not be able to go any direction, and then you'll have to go a different direction.
Okay.
All right. Let's see.
So the way you write your can't navigate, well, the points, like the +1, -1, does that matter?
The order? The order does not, in the end, the order does not matter. That's just which direction you wish to try going first. This is still kind of like tail recursion. Because all those that I put, you do the work and then I do my recursion, but it's not pure tail recursion because tail recursion has a final call being recursive call. And this one we're actually doing recursive calls in the middle. But notice that all the recursion happens after your base cases and after the work. The work here is marking your position as visited. Are there any questions on this one? Any other questions about recursion? How would you do this iteratively? Actually, that's a good question.
I'm trying to think of how, like, how you would repeat it, but I know you definitely put can navigate within the flow.
No, you do want to call, you don't want to do a recursive call. In a for loop, it wouldn't really, in a loop, if you did one loop, you'd have to have a separate data structure telling you where you need to go next, or what values you need to check next. And we'll actually get to that with queues. Another good example with queues. Because this is the depth first version, and there's the breadth first version. But we'll get to that in a little while. We're not there yet. But there is a way to do it iteratively, and I'll show you how to do that later on in this class. You have to really use a queue and put all your positions of what you want to evaluate next, and you just keep adding to the queue. And when the queue is empty, then you're done.
What would you rather use, this or recursion?
The recursion is a lot simpler to write and easier for me to think about. But the breadth first version does have an advantage, and we'll get to that later on, namely that the breadth first, it basically scans evenly throughout the maze, while depth first tries to go as far as it can and then jumps back up. So these are different types of searching. But the depth first one, I think, is a little easier to code than breadth first. The depth first also makes more sense to us because that's how we would do it. We wouldn't do a whole, like, trying to scan all the different paths at once. We would just scan one path at once and then jump back and keep going. Just different ways to solve the problem. We'll talk about more later. Any other questions about this? Is recursion a little clearer now? Great. All right. Now that we've done some coding, we're going to talk about another